Welcome to this lesson for Business Mathematics, Math 16269. If you need to reach me for any question or information, I can be reached by email at emily.brown3@sheridancollege.ca. For this course, you'll need a Business Mathematics in Canada e-text and associated Connect platform for your homework completion. And the mandatory required calculator is the Texas Instrument BA2 Plus Financial Calculator. This is the calculator with the financial keys. We're going to be looking at using them more in the second half of the semester, including many of the internal functions. Please check Slate frequently to keep up with course information and news announcements. And of course, Connect, make sure you're on that Connect platform for your homework assignments. So now we're moving away from the earlier concepts we looked at in the first half of the semester. We're moving on to compound interest, one of the most important things you'll learn in this course because it does impact both your professional and your personal life with respect to investing and also taking out loans, mortgages, car payments, car loans, business loans, and so on. So in today's lesson, we're going to be looking at the basic concepts of compound interest. We're going to be looking at finding future value. Again, we need to be mindful of the time value of money, that money today is not the same value as money yesterday or tomorrow. So we're going to be looking at how do we find future value or maturity value, same meaning, different words, and the present value of amounts of money. And again, using the financial calculator to do that more easily and efficiently. So the first thing is the basic concepts around compound interest. What is it and how is it different from simple interest? So if we start to compare simple interest to compound interest, we can see that simple interest and compound interest has a principal amount of money, right? That lump sum of money that you borrow or invest. There is a time component to both simple and compound interest. With simple interest, it's expressed in units of time, such as days, months, or years. And with compound interest, the time is expressed as the number of times that interest is calculated. So that's compounds per year. With respect to interest rate, in simple interest, you have a unit of time, so interest per day, per month, per year. And in compound interest, interest rate reflects per calculation of interest. So the interest rate per each compounding period. When is the interest placed into the account? With simple interest, it's simply placed in the account calculated and placed in the account at the end of that transaction's time frame. Remember, simple interest was generally used for short-term loans or short-term investments of a year or less, whereas compound interest, it is calculated and placed into the account with every calculation of interest. And we're going to look at that with respect to compounding frequency, how many times interest is calculated and deposited. If we look at this graph, we are looking at a principal of $1,000 being invested, say. And if we looked at the simple interest investment, we have $1,000 invested at 10% for 25 years. Okay, this is a bit of a longer span for a simple interest calculation, but we can see that the simple interest being calculated takes on the form of a linear function. It grows linearly, meaning that the interest is only calculated on the principal. It is never calculated on the interest when we're looking at simple interest. So the amount of interest year over year will be the same, and the principal will be carried forward. At the end of that 25 years, you can see that the amount in the account will be $2,500. A rather sad set of growth terms to go from $1,000 only to $2,500 over a 25-year period. By comparison, if you invested that $1,000 at 10% interest for 25 years in a compound interest setting, you would see that the growth of the money in the account grows what we call exponentially. It starts off slow, and in fact, in the first year, the amounts of money in the account for both simple and compound interest would be the same. But you can see that once that first year's interest is included and interest is earned on the principal and interest, you can see that that growth takes off quite significantly. And after 25 years, that $1,000 would be worth $7,334.71. If we look at this bar graph, we can see that how this works with compound interest, where we're converting interest to the principal at the end of each compounding period. So in this first bar, we can see that we have $100, and at the end of 1 year with the interest applied, we have $1,000. At the end of that year, we now have $1,000 plus that $100 interest. So for the second year, the interest is calculated on $1,000 plus that $100 that was earned of interest in the first year. And so for the second year, the calculated interest will be $110. Now we add $110 to $1,100, we have $1,210, and that is the calculation of interest for the next year, in which case the interest calculated is $121. And so the principal for that fourth year will then be $1,210 plus the $121. And you can see that the principal that the interest is calculated on grows by the principal plus the interest from the previous year. Let's look at some of the things that impact the effect of compound interest. Even with simple interest, if you had a higher interest rate, that would certainly impact the interest that was owed or provided in an investment. But with an exponential growth, as we see in compound interest, the impact of a higher interest rate is even more significant. This graph in particular shows the outcome of investing $1,000 over 25 years at different interest rates from 3% through 15%. So let's have a look. The lowest line on the graph here is an investment of $1,000 for 25 years at 3% interest. This is compounded annually, and we're going to talk about compounding frequency. But in order to compare, we need to have that compounding frequency the same. So here we're looking at annual compounds, and at the end of 25 years, that $1,000 will be worth $2,093.78. If we look at 6%, just a change in interest rate, we're going to see at the end of 25 years that $1,000 will be worth $4,291.87, and so on. Here's the amount, the value after 25 years at 12%. The value after, this was 9%. 17,006 cents if you invest or borrow at 12%. And here we see the highest where it's compounded annually, but with a very high significant interest rate of 15%. So that same $1,000 invested for the same amount of time can have a very significant end outcome at the end of 25 years based solely on the interest rate. Anything from $2,093.78 for an interest rate at 3%, all the way to $32,918.95 with an interest rate of 15%. I referred to compounding frequency a couple of times earlier in this lesson. So the compounding frequency simply means how many times interest is calculated and deposited over the period of a year. The compounding period refers to how many months or what term, I guess, we're looking at. So compounding frequency is how many times in a year interest is calculated. So if we have a compounding frequency that is annual, another word for that is effective, and we're going to talk more about that in upcoming lessons. But what that means is the compounding frequency is 1, meaning that interest is calculated and deposited 1 time a year. So every year. So you can imagine if you have 4 years, you would have interest calculated and deposited 1 time in year 1, another time in year 2, another time in year 3, and a last time in year 4. So over a 4-year period at an annual compounding frequency, you would have 4 calculations and deposits of interest. The next most frequent would be semi-annually. So semi-annually simply means every half year. So a half year is 6 months, and there are 2 half years in 1 year. So the compound frequency there would be 2 times per year. The next most common frequency is quarterly. So there are 4 quarters in a year. Every quarter consists of 3 months. So here you can see 4 times a year, which relates to every 3 months in a year. The next most frequent is monthly. So of course there are 12 months in a year. So interest is calculated and deposited every month. So that's again more frequently. The next 2, you can see we have little asterisks beside. They are for compounding frequencies that are weekly or daily. And you'll know in any typical calendar year, you may have 52 weeks. In another calendar year, you may have 53 weeks, and so on. So that asterisk simply means that we are going to consider every year as 52 weeks. And that would mean that interest is calculated and deposited every week, 52 times in a year. Again, with the daily compounding, we can have 365 days, or every 4. With our leap year, we would have 365 days. But the general consensus is we're going to use 365 years as our basis, and that would mean interest is calculated and deposited every day. In a prior slide, we looked at the impact of simply changing the interest rate, and we saw that the higher the interest rate, the higher the outcome of the investment or loan, the higher the future value. In this case, in this graph, we're looking at the impact of just changing the compounding frequency. So how frequently interest is calculated and deposited while keeping the interest rate the same at 15%. So we can see that here we have $1,000 being invested for 25 years at an interest rate of 15%, with the compounding frequency changing. So the lowest line here, resulting in $32,918.95 after 25 years, is with an annual compounding. So only calculating and depositing interest 1 time of year. The next highest would be semi-annual, where it's deposited 2 times a year. So after that first 6 months, then interest will be calculated on the principal and the interest of that first 6 months. So you can see that the growth is greater, resulting in an amount of $37,189.75. If we look at the most frequent compounding daily, so 365 times in a year, we can see that that results in the most significant growth, $42,488.34 after 25 years at 15%. So we need to think, what are the features we would want if we were investing or we were borrowing at these interest rates and these compounding frequencies? The choices you make with compound interest will be made depending on whether you are investing or borrowing. Same as simple interest, really. If you are investing, you're going to want to have your principal growing continually so that you earn more interest. And longer time frames are more desirable. The more often it compounds, the more principal that can earn interest. Daily compound would be perfect. And the higher the interest rate, the more you would earn. You want your interest to earn more interest. However, if you are borrowing, well, the simple interest would actually be more beneficial. You don't want interest being converted to principal. You want the lowest rate possible so that you pay less. The less often it would compound, the less principal that can earn interest. So an annual compound would be best. You don't want the principal to grow and earn more interest. So short time frames are more desirable. Here we're looking at a concept called periodic interest rate. The periodic interest rate is actually calculated within your financial calculator, and it's found by dividing the interest per year, so that would be your interest rate, over the compound frequency. And the compound frequency, again, remember, can be annual, semi-annual, quarterly, monthly, weekly, daily, and so on. If we were to calculate it manually, this would be a great visual to help you understand how to rearrange the formula for finding either periodic interest, nominal interest rate, or compounding frequency. Let's look at a few simple concept questions. If you're investing money, what interest features should you look for? If you're borrowing money, what interest features should you look for? Of 10% compounded semi-annually or 10% compounded monthly, which would earn the most interest? If you invested a principal amount at the same compounded interest rate for 20 years, would the amount of interest earned in the second 10 years be less than twice, exactly twice, or more than twice the interest earned during the first 10 years? If you're having difficulty answering these questions, check the previous slides. Here's another couple of questions to ponder. John has an interest rate of 4% compounded annually, while Dwayne is earning 8% compounded annually. If both people place the same principal into their investments for 25 years, would Dwayne have twice, less than twice, or more than twice as much money as John? Which one of 10% simple interest or 10% interest compounded annually earns more interest over time? Over time being the key word there. Which one of periodic interest rate or the nominal interest rate is always at least as large as the other? Again, refer back to the previous slides if you can't answer these questions easily. Let's look at a few calculations that we might make if we were looking at compound interest. And one of the things is the periodic interest rate, the interest rate per period. And again, we have this triangle to help us navigate through the calculation and using the algebraic formula. So here we're looking at periodic interest rate. Again, it's defined as interest per year divided by compounds per year, or compounding frequency. So here's their first question. It says calculate the periodic interest rate corresponding to 10.5% compounded annually. So this 10.5%, that would be your IY, and you're compounding annually, which means one time per year. So our periodic interest rate in this case would be 10.5%, or 10.5 divided by 1. The second part asks us to find the periodic interest rate of 9.75% compounded semi-annually. Again, IY divided by CY. And semi-annually simply means that you are compounding interest 2 times a year. So that would be 9.75 divided by 2, which would be give a periodic interest rate of 4.875 per half year. So 9.75 divided by 2. C says we have 9% interest, IY, compounded quarterly, so 4 times a year. So that would be 9 divided by 4, or 2.25% per quarter. D asks us to find the periodic interest rate of 9.5% IY compounded monthly, which is 12 times a year. So we would have 9.5 divided by 12, which would give you 0.7916 repeating percent per month. Here, using the same formula relationship, instead we're asked to find the compounding frequency, so the number of times per year interest is calculated and deposited, and that is called our CY, compounds per year. We can see if we use that little triangle that compounds per year are found by dividing IY, or interest per year, by the periodic interest rate, I. So it says for a nominal interest rate of 8.4%, what is the compounding frequency if the periodic interest is 4.2%? Okay, so we're going to be dividing IY by I. So here it would be 8.4 divided by 4.2, and that would give you a value of 2. So that means 2 times a year, or semi-annual. In B, you have 8.4% as your nominal interest, and as your periodic interest, and the nominal interest is 8.4. So in this case, we have 8.4 divided by 8.4, giving a value of 1 compound per year, which we call annual or effective, 1 time per year. If we look at C, we have a periodic interest rate of 2.1%. So again, we have IY of 8.4, that's your nominal interest rate, divided by 2.1, our periodic interest rate, gives us a value of 4, or 4 times a year compounded. That's quarterly frequency. In D, we have a periodic interest rate of 0.7%. And again, we have our nominal interest rate of 8.4. We're dividing by our periodic interest rate. Here we have a value of 12. And again, 12 would indicate that interest is calculated and deposited 12 times a year, or monthly. And lastly, let's look at how we find that last variable, IY, or nominal interest rate. We can see if we use the triangle for reference, we would be multiplying the periodic interest rate by the compounding frequency. So in A, we have the periodic rate is 1.75% per quarter. So our IY would be 1.75 times 4, giving us a nominal interest rate of 7%. In part B, we have a periodic interest rate of 0.83 repeating, and so per month, and so our nominal interest rate would be the periodic interest rate times 12, and that would give us a nominal interest rate of 10% compounded monthly. So we're going to look at the first ways that we can calculate using compound interest, and that is the future value or maturity value, whether it's of an investment or a loan. And in many ways, it's like simple interest in that you are looking at the value of money at some time in the future. The very simplest future calculation scenario is for compound interest when all the variables remain unchanged throughout the transaction. So that would mean that through the entire time period of this calculation, the interest rate would stay the same, the compounding frequency, and so on. First, you would need to know how many times interest is converted to principal throughout the transaction so that you can calculate the total compounds n. So that would be the number of compounds per year times the number of years that is in the calculation. Then you'd be able to calculate future value. Here, n, or the number of compounds total over the course of the investment or the loan, is found by multiplying compounds per year times the number of years. So if we had an investment that was invested for 5 years at a compounding frequency of 2 semi-annual, there'd be 2 compounds in the first year, 2 in the second, 2 in the third year, 2 in the fourth, 2 in the fifth, for a total of 10 compounds, or 10 is your n over the period of 5 years compounded semi-annually. As an example, as you know, interest compounded would be an exponential function, and here you can see in the formula for future value, n is the exponent to which PV and 1 plus I, these interest terms, are applied. I being the periodic interest rate, PV being the present value, and this interest set of interest terms applied to that value in order to find your future value. If you haven't utilized a timeline while we worked on simple interest, it is even more imperative now that you do so, because it allows a visual of where money is moving in time, whether you're finding the future value or the present value. So start off, draw a timeline. If you're using the formula, calculate the periodic interest rate, but I encourage you to use the calculator so that periodic interest rate will be calculated internally. Calculate the total compounding periods. How many years times how many times interest is compounded in that 1 year period, and then you're able to calculate the future value. Well, the future value formula may be used and useful as demonstrated here. I'm going to encourage you to get comfortable using the features in your BA2 Plus financial calculator. So I've included a little template here that contains all of the variables that you're going to need in order to utilize these features and your calculator effectively. So while we're still looking at simple calculations with one value of money moving in time, I'm going to let you know that there's no mode yet and zero payment, meaning there's zero recurring payments. In weeks to come, we're going to be looking at using different modes to calculate, and in fact a regular recurring payment like a mortgage, a loan, or a car payment. Until now, these are the only variables that we're going to need. It says here that we're going to be calculating the maturity value of an investment, so we're going to be looking at this future value. That's what we're trying to find. If we go across the variables from left to right, we see PY and CY. PY and CY mean payment per year and compounds per year. Right now, the only payments per year are the interest payments that are going in. So payments per year are the same as compounds per year. If we look at the question, we can see that the compounding frequency is semi-annual. So our CY and PY will be 2, meaning 2 times a year interest is calculated and deposited. The next variable is our n. We know that n is calculated by multiplying compounds per year times the number of years. Again, 2 times a year is the number of compounds, and it says here that this investment is 5 years long. So 2 times 5 would be 10. Our n is 10. Interest is given at 3.75. And we're investing money, so money is going out. So we're going to say that the money invested is $10,000, negative $10,000. And we're going to be able to compute or calculate our FV. On the next slide, we'll look at how we input these values into the BA2 Plus calculator. Here's the face of the BA2 Plus calculator. So if we look at our template with our values that we're going to be inputting, again, there's no mode at this time, so we don't have to worry about that. The first thing is PYCY, payments per year, compounds per year, and that is an internal feature. So the first thing that you're going to do is push second function IY, and above it you can see the little PY. Inside there you're going to see PYCY with arrows. So second function IY, you're going to put a value of 2, enter. PY, so arrows, PY2, enter. And then again, second function, and then quit. And then you're out of that feature there. Okay. Let's back up a bit. The next thing we're going to look at is n. So our n we calculated was 10. So we're going to put 10 and then push the n button. There's no need to enter. So 10 and then n, and it will show n equals 10 on your screen. The next thing we're going to put in is the IY, the interest per year, which was 3.75. So 3.75, select the IY button, and it is inputted. You don't need to push enter. PV, remember it's minus 10,000, so 10,000, and then the plus or minus button on the bottom of the calculator here. And that will put a value of minus 10,000. It's minus because it's going out of our pockets. It's an investment. Payment is 0, so just put 0 payment, and we don't have to worry about that again until later in the semester. And then we're ready to find out what that future value is. We do that by selecting compute and then future value. And when we compute future value, we're going to find that the value of $10,000 in the future of 5 years at those interest terms will be $12,041.38. Let's have a look at this question where we're trying to compare two nominal rates of interest. The question reads, other things being equal, would an investor prefer an interest rate of 4.8% compounded monthly or 4.9% compounded annually for a 2-year investment? So just like the other questions we've done in this lesson, we're not going to worry about mode right now because it's not impacting us until later in the semester, and we have no regular recurring payments, so our payments will remain at 0. Let's have a look at this question. We aren't given a value, a present value, but we are given a way to compare these two interest terms. So I would suggest that we pick a present value of, say, $1,000. And let's see the impact of these investment terms on a value of $1,000. It is an investment, So I'm going to have our present value as $1,000 negative. So you're going to have to put $1,000 and then plus or minus on your calculator. It's minus a negative number because when you're investing, money goes out of your account or out of your pocket into some investment vehicle. Our PY and CY, payments per year and compounds per year, at this time, only the interest is calculated and inputted, so that's the only payment that's being received. So those things now, PY, CY, are the same. So we have two sets of investment terms. One at 4.8% compounded monthly, and the other at 4.9% compounded annually. So in the first case, we're going to have a payments per year and compounds per year of 12. Our N we need to calculate. We find that by multiplying our compounds per year times the number of years. In this case, we're told it's a 2-year investment. So our N in the first case here is 12 times 2, which is 24. Compounds 12 times 2 years, 24. Our IY is given as 4.8. Okay, and we're going to be computing the future value. In the second case, our N again would be calculated by multiplying compounds per year times number of years, but in this case, the compounds per year are 1. So 1 times 2 is going to be 2. Our IY in this case is a little higher at 4.9. And again, we're going to compute our future value and compare those two values. This is in an investor, so you're going to be looking at having the highest future value possible. And whatever that highest value would be, those are the investment terms or interest terms you're going to be taking on. Let's see which one produces the best results. So again, here's the face of our BA2 Plus calculator. The first thing that you're going to want to input is your payments per year and compounds per year. Remember from our last example, we have second function and IY. That's where we're going to be putting in those particular terms or conditions. In the first case, it's 12. Then we're going to put 24 and N. IY is 4.8, so 4.8 IY. 10,000 plus or minus is our PV in the first example. Payment is 0, and our FV, we're going to compute FV. Okay. In our second case, of course, our PY and CY are now going to be annual, so 1 time per year. So again, we're going to go back into that second function IY, change the conditions to 1 for CY and 1 for PY using these arrows up and down. Then we go back to our financial keys, again across that top part of the calculator. Our N, in this case, our N is 2, so we input 2 and then press the N button. Our IY is a little higher in this second instance, so 4.9, and then select IY. Our PV is the same at minus 1,000, so it would still be there, or you can input it again, 1,000 and then plus minus button. 0 payment, that's still the same, and then we're able to compute our future value. Here we can see the calculations that you'd be doing if you were using the formula, and we can see that with conditions of 4.8% compounded monthly, the future value is $1,100.55. With the second conditions, an interest rate of 4.9% compounded annually, the future value is $1,100.40. So here you have a higher future value, marginally higher, 15 cents, but you're an investor and you want to have the highest future value, the highest output possible. So you would check that, you would choose that as your option for investing. We could see that the higher compounding frequency of 12 or monthly outweighs that slightly higher interest rate in the second example. In this question, we're looking at calculating the maturity value when the interest rate changes. So this is no longer sort of a simple calculation. We're going to have to consider where these changes take place, and we're going to have to use time segments in order to calculate the future value. It says here that George invested $5,000 at 4.25% compounded quarterly. But after 18 months, the rate changed to a 4.75% compounded semi-annually. What amount of money will George have 3 years after the initial investment? So our best thing to do is draw a timeline. We're going to draw a timeline that extends out to 3 years, because we're ultimately looking at the future value here at 3 years. We're starting today with an initial investment of $5,000. And after 18 months, so that will be after a year and a half, after 18 months, the interest rate goes from 4.25 quarterly to 4.75 semi-annually. Okay. So what we're going to have to do here is break this up into time segments. So we're going to have to find the future value of the $5,000 at 18 months under these conditions, 4.25 quarterly. And at this point, we're going to make this future value equal to the present value for the next time segment. We got used to doing this type of calculation using simple interest, and now we're just doing it again with compound interest. Then we're going to find the future value of that present value at 18 months. We're going to find the future value at 3 years. And we're going to then change the interest terms to 4.75 compounded semi-annually. So let's have a look at our variables. Again, our mode is not relevant right now, and our payments are 0. In the first segment, so I'm going to mark this as 1 and 2. So in the first segment, we have a PY and CY of 4. Our N, again, we calculate that by compounds per year times the number of years. In this case, we have 18 months, so that's a year and a half. You can also use 18 over 12 as your time frame. So here it's going to be 4, because it's quarterly, times 18 over 12. And we're going to have an N value of 6. 6, right? Our interest in the beginning is 4.25. Our PV is minus 5,000. Again, it's invested, so minus 5,000. And we're going to compute the future value. This future value with a sign change will become the present value for the next time segment. Our PY, CY for the next time segment is semi-annual, so that will be represented by 2. Our N will be 2 times, again, 18 months to 3 years, right? So that's an 18-month difference. And so our N will be 2 times 1.5, or 3. Our interest goes up to 4.75. Our PV, as I said earlier, is going to be the future value for the first segment with a sign change, so plus or minus. And then we're going to be able to compute the future value at the final stage after 3 years of this investment. Here you'll see some of the calculations here for N, for example. in the first part of this investment, 3 for the second part, $5,000 being the initial PV. So that would take us to here, and then our second segment here to 36 months or 3 years. And using our financial calculator, we would have determined that in the first time segment, the $5,000 was worth $5,327 and 34 cents. Again, you're going to try and keep as many decimals as possible to increase your accuracy. And then you can see that this future value becomes the present value for that second segment. And if we input those values on the prior slide into our calculator correctly, we'll find that after 3 years, this $5,000 is worth $5,716. So at the end of 3 years, George will have that amount of money, $5,716. In this question, we're going to be looking at the balance owed after payments on a compound interest loan. In this case, Faye borrowed $5,000 at an interest rate of 3% compounded quarterly. On the first, second, and third anniversaries of the loan, she made payments of $1,500, of course reducing what she still owed. So what payment made on that fourth anniversary will extinguish the debt? And extinguish simply means to have zero debt left, to pay off the loan. So how would we calculate that? We're going to have to calculate the future value at each of those anniversary dates and then reduce that amount by $1,500. Continue to the next anniversary date, do the same, reduce it by $1,500, and on the third anniversary date, reduce by $1,500, and then continue to calculate the interest until we have the future value still owing on that fourth anniversary. That will be the amount she'll need to pay in order to extinguish the debt or have zero debt owing. Here I've placed a single template of the variables on this page, but we can use it almost as a heading in order to use it for this particular example. Again, we don't have to worry about mode, and our payments are zero because they are regular. We'd have no regular recurring payments. So the conditions are fairly easy. We have $5,000 that was borrowed, and because it's coming to us as something borrowed, we're going to use that as a positive value. We have an interest rate of 3%, and it is compounded quarterly. So our PY and CY will be 4. Now we're looking at future value over a series of 4 years. So our N, in fact, while it's calculated as CY compounds per year times the number of years, we're going to be looking at year after year after year. So we have a quarterly compound, but only for 1 year. So each of those N values will be 4. Okay. So for our first year, year 1, I'm going to say we have those values. PY, CY 4, N is 4, IY is 3, PV is 5,000. We're going to compute our FV. At this point then, for our year 2, we're going to take this future value. We're going to subtract that payment of $1,500 that she's going to put in. After we change the sign, so plus minus, and then subtract the $5,000, that becomes the PV for the next year. These things will all stay the same. 4 will stay the same, 4 for N will stay the same, 3 will stay the same, and we're able then to compute our future value here. Okay. When we find that future value after the second year, again, we're going to change the sign, plus or minus. We're going to subtract $1,500 because that's the payment that she's making on every anniversary date. That becomes our PV for the next segment. Again, our IY is still 3. Our N is still 4. That's quarterly payments for a year. Our PYCY is 4, and this is for our third year. Okay? And we do that again for our fourth year. Okay? 4, 4, 3. Again, plus or minus. We're going to then subtract 1,500. That becomes the PV for that last segment. And we're going to compute FV. And that is going to show the value that's still owing after the end of those 4 years with those terms of payment. And here we're going to find that our final FV is $856.35. And that is what Faye would have to pay at the end of that fourth year in order to extinguish or eliminate that debt, to bring it to zero. Here you can see the example of a timeline where we're showing what's happening over the course of those 4 years, right? With the 3 payments down and with the FV becoming the PV of the next segment. Here you can see the calculations, or after the first year there's a value of $5,151.70, a payment of $1,500. This new future value becomes the present value for the next segment, and so on until you get to the final year, again when that last amount owing is $856.35. In this question, we're looking at equivalent value of 2 scheduled payments. Again, we did this type of calculation when we were looking at simple interest. And one of the most important things was to draw a timeline in order to understand, are we finding present value or future value based on when that new equivalent payment would be made. So here we have the question. It says, Small Claims Court has ruled in favor of Mrs. Peacock. She claimed that Professor Plum defaulted on 2 payments. Defaulted means that the payment was scheduled and they weren't made. The 2 payments of $1,000 each. One payment was due 18 months ago, so 18 months in the past, and the other was to be made 11 months ago. What is the appropriate amount for the court to order Mr. Plum, Professor Plum, to pay immediately if the court uses 6% compounded monthly for the interest rate money can earn? If we have a timeline, or if we draw a timeline, which we should, we're going to be looking at today as being the court order. This is when we're looking at how much is owed that would be an appropriate amount. 18 months ago, there was a value of $1,000 owed, which was not paid. 11 months ago, there was another $1,000 payment that was not paid. Okay, so we're going to be finding the future value of those 2 payments today. Okay, there's a couple of ways to do this. I think really the easiest way is to bring both of those payments to the present day. So I would find the future value of this $1,000 with 11 months interest owing, and I would also find the future value of this $1,000 that was owed 18 months ago. At the end here, I would be adding those 2 future value amounts to the total, that one equivalent payment that would be equal to 2 scheduled payments. And the interest paid on this would be 6% compounded monthly for the entire time that we're dealing with, from 18 months and 11 months to today. I've placed 2 templates here. The one will be for the $1,000 that was owed 18 months ago, and the second will be for the amount of $1,000 owed 11 months ago. Again, we don't worry about mode right now until later on in the semester, and we have no regular recurring payments, so our payment is 0. Recall that our interest rate was 6%, and it is compounded monthly, and again, still our payments per year are only the compounded interest that is placed in the account. So our CY and PY are the same, and they're compounded monthly, so that is 12. Now, we have to look at this N value. Remember, we have one payment that was 18 months, and it is being paid today. So we have 18 out of 12, and our CY is 12. So here our N will be 18. For the second segment, or the second payment, sorry, of $1,000 due 11 months ago, but paid today. Again, we have our CY of 12 for 11 of 12 months. So that makes our N 11 in this case. Our PV in both cases is $1,000. We're going to compute the future value of each of those $1,000 payments, and then we're going to add them together to make that one single amount paid. When we do that calculation, we find out that for the 18-month calculation, the value of that $1,000 will be $1,093.93. And the value of $1,000 11 months ago in today's dollars is $1,056.40. We're going to add those together to make that one single payment of $2,150.33. Just as we did with simple interest, we are able to calculate the present value using the compound interest terms. We've just done a bit of work with future value, so let's see how the present value works. You can see that present value is embedded in that future value calculation, where we find the future value by multiplying the present value by these interest terms. And so for the present value calculation, we would simply be taking that future value and dividing by the interest terms. Best practice is to always draw a timeline. If you haven't become comfortable with one yet, please do so. You would calculate the periodic interest rate if you intend to use the formulas only, but we're going to be using our BA2 Plus financial calculator. You would calculate the compounding periods, N, by multiplying CY times the number of years, and then we'd be able to calculate the present value. As a reminder, the future value is found by taking the present value and multiplying that by that interest factor. This increases the single payment by the interest earned. Present value, on the other hand, takes the future value and divides it by the interest factor, and this removes the interest and decreases the single payment. In this present value calculation, we're looking at how much one would need to invest in order to reach a particular future value. Imagine that you have tuition to pay, or you want to buy something big like a car, or you want to take a trip. You need a certain amount of money in the future. Finding your present value calculating your present value will allow you to know how much you should invest in order to have that value of money in the future available to you for your uses. So here we have a question. It says, if an investment can earn 4% compounded monthly, what amount must you invest now in order that that accumulates to $10,000 after 3.5 years? Okay, so what does that say? Our mode is still not necessary until later on in the semester, and we have no regular recurring payment, so payment of 0. Our PY and CY, so compounded monthly, that's where you're going to find that amount. And again, they can only be very specific: annually 1, semi-annual 2, quarterly 4, monthly 12, weekly 52, or daily 365. So here we have monthly, that will be 12. It's for 3.5 years, so our N will be CY, compounds per year, times the number of years. So that will be 12 times a year for 3.5 years. So that will give us an N of 42. Our IY is 4% interest. And we're looking for our PV. How much do we need to invest now in order to have $10,000 in the future? When we make that calculation, we find that the present value, the amount we need to invest to have $10,000 in 3.5 years, is $8,695.61. That would be negative on your calculator, as it would be invested, so that would be money out of your pocket. In this example, we're calculating an equivalent payment at an earlier date, so that would be present value. We have a payment of Mr. and Mrs. Nguyen. Their property taxes of $5,450 are due on July 1st. What amount should the city accept if the taxes are paid 8 months in advance and the city can earn 3.6% compounded monthly on surplus or extra funds? Let's find out what our variables are and how we're going to make this calculation using our BA2 Plus calculator. Again, our mode is not necessary right now, and we have no regular recurring payments, so they continue to be 0. Our PY, CY, remember those are the same because the only payments right now are interest payments, so related to compounds per year. Our compounds per year are monthly, so that's going to be a value of 12. Our N, okay, it's going to be for 8 months in advance. So our N is calculated by multiplying CY by the number of years. In this case, it's a portion of a year. So we have 12 times 8 over 12. That's 8 months out of 12 years. So our N will be 8. IY is 3.6%. Our future value is the value of the property tax on July 1st. So that will be $5,450. And we're trying to find out what the present value, or what value is that tax payment if it's paid 8 months earlier. Remember that a present value is always going to be less than a future value. And when we do the calculations on our calculator, we find out that the value 8 months earlier at those interest terms will be $5,320.95. This is the amount that the Nguyen family needs to pay in order to have an equivalent payment of those tax payments due on July 1st. We're looking at this next example where we're asked to calculate an equivalent value of 2 payments. Again, remember that the best tool you can use to determine what action you're going to take in a question like this is to draw a timeline. Straight line. We have two payments of $10,000 each. I'm going to say that we're going to mark today on the timeline. $10,000 each to be made 1 year from now and 4 years from now. So 1 year and 4 years. Try and make your timeline so that the numbers are kind of on a scale, right? So then it says that, it's $10,000. I need to write that. Okay. Interest is 3% compounded monthly. Okay. What single payment 2 years from now would be equivalent to the two scheduled payments at 1 year and 4 years? I'm going to pick up a different colored pen here and mark 2 years on this timeline. So we can see when 2 years is put on the timeline in the correct place that it is later than the 1 year. So we're going to be finding the future value of that $10,000 that was due in 1 year. And we're going to find the present value of the $10,000 that was due 4 years from today. So we're going to be looking at the time difference between those two payments. This is 1 year, from 1 year to 2 years, and from 4 years back to 2 years, that will be a 2-year difference. And then we're ready to put these variables into our templates in order to input them into the calculator and make our final calculations. When we find the future value and the present value of these two amounts, we add them together in order to find the total that would be owing at 2 years. Okay? If we look at our templates and where we're going to place our variables, again, our mode is not necessary and our payments are 0. In the first example, or first part, we're going to be looking at the $10,000 that is due in 1 year, but we are now making an equivalent payment at 2 years. Our payments per year, let's see, we have 3% monthly, so our PY and CY is 12, and it stays the same for the other payment, so we can make that note right away. Our N, now for the first segment, or the first calculation, we're finding the future value when moving money from 1 year to 2 years. So our CY times the number of years in the first case will be 12 times 1, which makes an N of 12. Our interest rate is 3%. In the second case, we are moving money from 4 years in the future to 2 years, a difference of 2 years. So we have CY of 12 times 2, our N will be 24. So in the first case, we're finding the future value. We're moving $10,000 from 1 year to 2 years. So we're finding that future value, and the amount we're moving is $10,000. Okay? In the second case, we are finding the present value of $10,000, and the $10,000 is valued at 4 years from now, so we're finding the PV. Then we're going to take those values we find here, the FV and the PV, and we're going to add them together in order to find the total single equivalent payment of those two payments that will be paid at 2 years from today. When we do our calculation, we find that the $10,000 moving 1 year later will be valued at 10,304 and 16 cents. And the $10,000 that we're moving back in time from $10,000 in 4 years will become $9,418.35. We take those two together, we add them up, and when we do, we find that the amount owing totals $19,722.51 at 2 years. This question simply asks us to look back at our last example and determine why the recipient of these two payments should be indifferent about receiving the scheduled payments and receiving the replacement payment. Indifferent simply means they don't care, it shouldn't matter, but why doesn't it matter? Why doesn't it matter economically? The recipient ends up in the same economic position with either alternative. Then he shouldn't care which alternative is used. So how are we going to calculate how much money the recipient will have 4 years from now with each alternative, assuming that any amounts received are invested at 3% compounded monthly? Let's look at the two alternatives as they are presented in the two following timelines. We're going to look at the value of the money at 4 years. We already know that one of the payments was $10,000 at 4 years, and there was a payment of $10,000 at 1 year. We're going to find the equivalent payment of that $10,000 at year 1, and we're going to find out what the equivalent payment is 3 years later at year 4. The alternative is to take that value that we have calculated of our two payments and the single equivalent payment in our last question, and we're going to move that amount to 4 years. And we're going to see if they are the same or if one is higher than the other. I suspect if we did our calculations correctly, then they should be equivalent at 4 years. So here is a quick summary of the calculation that we would make. We find the future value of that $10,000 at year 1, and we add the $10,000 already existing at the 4th year. We find that the total at year 4 is $20,940.51. If we take that full equivalent amount that we calculated of $19,722.51, and we move that entire amount 4 years later, we see that we have an identical amount of $20,940.51. Therefore, the replacement payment is economically equivalent to the scheduled payments. So the recipient should not care in which way he is paid. In this question, we are asked to calculate the original amount of a loan based on payments that we are told. Here we have 3 payments of $1,500 each, plus a different amount, a different final payment of $856.35. These payments were made on a loan at 1 year intervals, so that's 1 year apart after the day of the loan. The interest rate on the loan was 3% compounded quarterly. What was the original amount of the loan? I'm going to draw a timeline because that will help us determine what we're looking at here, hopefully. So, some amount of money was taken out at the beginning. That's going to be our question here. At 1 year, I'm going to divide it like this so it's kind of evened out. At 1 year, $1,500 was paid back on the loan. At year 2, so at regular 1 year intervals, $1,500 was paid back. Again, at year 3, $1,500 was paid back. Those are 3 payments of $1,500. And the last payment to pay off this loan was $856.35. That's what we're drawing up. Okay, so we're trying to find out how much was borrowed in the beginning. So we're going to be looking at present value. We're removing interest and we're moving money back in time. We find here PV1, here PV2, this third 1,500 will be PV3, and 856.35 will come back as well to present time, and that will be PV4. We're going to add each of those present value calculations, and they should sum to the total value of the loan at the beginning. Let's see, we have interest rate of 3%, compounded quarterly. So we're going to need 4 templates. I can pull 4 templates over for us to fill out for each of those 4 present value calculations. I've pulled together 4 templates here for our variables. The reason for that is we have 4 payments that are in the future value that we're finding the present value for. They are payments made at 1-year intervals, 3 of those at $1,500, and the last one, which is $856.35, and that's from year 4. And we're moving those 4 payments to today's value, and then we're adding them up together to find the total loan that was given. Again, our mode is not necessary right now, and we don't have regular recurring payments like a mortgage or loan payment. Okay. Our interest rate, I believe it was 3% quarterly. So I'm going to just put that up there to remind me. 3% quarterly on all of these payments. So we can put 3% in each of the IY places here. Our PY, CY will be the same. And in fact, once you have these variables inputted, you don't need to redo them as long as they're the same for the next calculation. So when you put 4 in as your CY, PY into that internal feature, you can just leave it there because we're using that same value for each of the calculations. Okay, so for the first, I'm going to put here $1,500, $1,500, $1,500, and here, what did we say? $856.35. So we're finding the PV of each of those values, and then we're going to add them up, and that will be the amount of the original loan. So in the case of the first $1,500, if we say that was the value at 1 year, we're going to be moving it back just 1 year, and our N calculation is CY, or the compounds per year, times the number of years. So in this case, we have 4 times 1, which will give us an N of 4. For the second one, so this $1,500 here, we're moving it back 2 years. So in this case, it will be 4 times a year for 2 years. That will give us an N of 8. This one we have 3 years in the future. We're moving it back 3 years. So our N will be 4 for 4 compounds per year times 3 years. That will be 12. And our final calculation of present value, it's $856.35. It's moving from 4 years in the future to present value today. So that'll be 4 for compounds per year times 4 years. That will be 16. And now using our BA2 Plus calculator and inputting the values correctly, each of those present value calculations will be simple to do. So I'm going to pick up a red pen and I'm going to put those values in. The $1,500 that was paid or owed on the first anniversary or first year, that will be equal to $1,455.83. The second $1,500 2 years in the future in today's dollars will be $1,412.96. The $1,500 payment 3 years in the future in today's value would be $1,371.36. And then this $856.35 has an equivalent value today of $759.85. When we total those three together, we see that they total $5,000. So that's the original amount of the loan, $5,000 paid back in 3 payments of $1,500 and that last payment. Here is a quick table of the calculations using the formula, showing the same values that we found using our calculator. And again, the total loan was $5,000. Those are all the questions we have today in our introduction to compound interest. Please make sure that you follow along and that you do the questions in Connect in order to give you extra practice. And if you have any questions, don't forget you can always email me, emily.brown3@sheridancollege.ca.